Hi everyone, here are your video solutions for today's homework. We're going to start with number 7 from section 5.1. Question asks, is lambda equals 4 an eigenvalue of that matrix? If so, find one corresponding eigenvector. All right, so we're examining lambda equals 4. We need to ask ourselves, does the equation ax equal 4x have solutions? We're interested in whether or not it has non-trivial solutions. So we're going to do this by taking ax minus 4ix equals 0. We're going to rewrite that as a minus 4I times x equals 0. Now we have something that we can augment in ref. So let's go over to the calculator to explore that. I'm going to define the matrix A as it's given in the text. So 3, 0, negative 1, 2, 3, 1, and negative 3, 4, 5. I'm going to take A minus 4 times the 3 by 3 identity. That gives us this matrix. We want to see what are the non-trivial solutions to this. So I'm going to ref that matrix augmented with the 0 vector. We end up with that, which is good. We don't see a pivot in every row and column, which means that we do have a non-trivial solution. So I'm going to pull that over to our other page and we'll work with it. All right, so after refing we get this. That means that x1 equals negative x3, x2 equals negative x3, and x3 equals x3. So a basis for this eigenspace, or one particular vector that is an eigenvector, would be negative 1, negative 1, 1. And I'm going to go confirm that by taking a times that vector and showing that it is indeed 4 times the original vector. So that vector is negative 1, negative 1, 1, and that gets me negative 4, negative 4, 4. So that's confirmation that that vector is indeed an eigenvector. So the answer to that question is yes. Next, we're going to do 10. Directions here say find a basis for the eigenspace corresponding to each listed eigenvalue. For number 10, we've got a 2 by 2 matrix, and again, we're dealing with the eigenvalue of 4. So here's the matrix, 10, negative 9, 4, negative 2, and lambda equals 4 is our eigenvalue. So we're going to do the same approach. I'm going to define matrix A, be the 2 by 2 matrix, 10, negative 9, 4, negative 2. I'm going to take A minus 2 by 2 identity, and it's 4 times the 2 by 2 identity. We're going to augment and ref that. So here is the matrix which is going to show us the solutions. There we go. All right, so this means that x1 equals 3 halves x2, and x2 is free. Great, we do have non-trivial solutions. We could use the vector 3 halves 1. I'm just going to scale that up and use the vector 3, 2. So this is a basis for the eigenspace that's associated with lambda equals 4. Again, I'm going to test that by taking the original matrix times 3, 2. Let's see what we get. We get 4 times, which we do. Yep, we get 4 times the original vector, so that's confirmation that that vector and any scalar multiple of it is in the eigenspace for lambda equals 4. For example, if I took 6, 4, we should get 4 times this as well. We should get 24 and 16, which we do. Great, let's take a look at 18. All right, for 18 it says, find the eigenvalues of the matrices in exercises 17 and 18. All right, so we didn't get to a particular theorem. If you look back to page 271, you'll see theorem 1, which says the eigenvalues of a triangular matrix are the entries on its main diagonal. That means in 18, because this is a triangular matrix, right, you've got zeros above the main diagonal, the eigenvalues are simply lambda equals 4, lambda equals 0, and lambda equals negative 3. Before we just go on and say this was a theorem that we didn't cover, I want you to think about why this makes sense based on what we did cover. Remember that we're trying to find when is the determinant of a minus lambda I equal to 0. If you take that matrix in 18 and you subtract lambda from all of the items on the main diagonal, you're going to get this. So 0, 1, 0, 0, 0, 0. Remember that if you find the determinant of that, that's a theorem that we do know. The determinant of a triangular matrix is the product of the things on the main diagonal. So we're basically saying, when is 4 minus lambda times negative lambda times negative 3 minus lambda equal to 0? When we solve that characteristic equation, we end up with lambda equals 4, lambda equals 0, and lambda equals negative 3. So it makes intuitive sense even if we don't have the theorem. Number 19. For A equal to that matrix, find one eigenvalue with no calculation. Justify your answer. Okay, we know right away that AX equals 0 has non-trivial solutions. And the reason we know this is because the columns are linearly dependent, right? Well, if AX equals 0 has non-trivial solutions, that means we don't need to subtract away any lambda. That means lambda equals 0 is an eigenvalue, and that's the one that we can find without any computation. Okay, that's it for 5.1. Let's take a look at 5.2. Going ahead to number 2 in 5.2. Okay, number 2 gives us the matrix 5, 3, 3, 5, and asks us to find the characteristic polynomial and the eigenvalues. All right, so I'm going to take A minus lambda I. Find the determinant of that. Since it's 2 by 2, it's nice and easy. We can do it by hand. All right, so our eigenvalues are negative 2 and 8. And that's all we had to find. Number 5. Similar question. We've got 2, 1, negative 1, and 4. Let's take A minus lambda I. So our characteristic polynomial would be 2 minus lambda times 4 minus lambda plus 1 equals 0. Okay, this means that lambda equals 3 is our only eigenvalue, and it has an algebraic multiplicity of 2. We'll talk more about all those multiplicity things in class. Okay, and then 15 and 18. Here's 15. For the matrices and exercises 15 through 17, list the eigenvalues repeated according to their multiplicities. This is making use of the theorem that we had again in the last section. This is a triangular matrix. So lambda equals 4 is an eigenvalue. Lambda equals 3 is an eigenvalue with algebraic multiplicity 2. And lambda equals 1 is an eigenvalue with algebraic multiplicity 1. I should have listed that for this too, algebraic multiplicity of 1. And then for 18, we've got, it can be shown that the algebraic multiplicity of an eigenvalue lambda is always greater than or equal to the dimension of the eigenspace corresponding to lambda. We know that from what we discussed in class. Find H in the matrix A below such that the eigenspace for lambda equals 5 is 2-dimensional. Okay, that's interesting. All right, so lambda equals 5. Let's take away 5 from all the things on the main diagonal. So 0, negative 2, 6, negative 1, 0, negative 2, H, 0, 0, 0, 0, 4, and 0, 0, 0, negative 4. Okay, so this matrix is A minus 5I, and we want the null space of this. So we want the null space to be 2-dimensional, which means we want 2 free variables. Okay, 2 free. All right, so let's begin by kind of re-refing this matrix, I guess. Put it into a form that makes a little bit more sense. All right, so we'll go 0, 1, -3, 1/2. I think I'll leave this row alone for now. Simplify this row down to that, and this row down to that. Okay. The first row, leave it alone. Second row, I'm going to take 2 times the first row plus the second row, zeroes that out. -6 plus h, and 2 times the first row plus that gives that a 1. Leave this one alone, and that last row can be zeroed out by just adding those last 2 rows. Okay, so we know that we have a leading entry. I'm going to highlight the pivot columns. This is a pivot column, and this is a pivot column. In order for that, so we have what we need at this point. This thing is non-pivot, which means we have one free variable, and this thing is non-pivot, which means we have another free variable, but that's only going to be non-pivot if h is equal to 6. So there's our answer. We need h to be equal to 6 in order for this to happen. Okay, we'll do more work with this in class. Thanks for watching. I hope that was helpful.